So we were looking to find an Euler-Lagrange equivalent for a functional with two independent variables, or dx and dy. Now we've got to this point here in the previous video. What we want to be able to do is we want to be able to separate out the value of eta from this equation, because we know that the value of eta doesn't equal 0. So whatever is left over once eta has been removed from this equation must be the factor that is equal to 0. So in effect this will become our equivalent Euler-Lagrange equation for a functional with two independent variables. Now the problem with separating out this eta is that we know how to separate out the eta here. We simply take out the brackets. But now we've got a functional with two independent variables, x and y. So in order to separate out this eta here from this part and the eta here from this part, we're going to use Green's theorem. So what follows over the next few minutes is a graphical derivation of sorts of Green's theorem. Now we don't need to get into it in complete detail, we just need to get access to the actual Green's theorem so that we can use it in the next video in order to separate out this value of eta. So let's go ahead and we'll look at Green's theorem now. So here's the statement of Green's theorem here. So we're going to go ahead and we're going to prove this theorem using an intuitive graphical method. So put simply, what this theorem does is it relates the surface integral, so in effect a double integral of some quantity here in brackets, with the single integral or the line integral of another quantity here within these brackets. So this here is nothing other than an extension of the fundamental theorem of calculus. The fundamental theorem of calculus relates the constant terms here with the integral of some related function. So if we were to extend this here up to two integrals here, we would be relating a surface integral with a line integral. Now we could extend on that again, we could put this on to three integrals, so we would be relating a volume integral then with a surface integral. But we don't need to get into all of those details, we're just looking to find a proof of this theorem here. So let's continue and we'll do that now. So let's start off with the fundamental theorem of calculus. We can take a function phi, and if we were to differentiate the function phi with respect to x and then integrate that from, say, the limits a to c by dx, then you're just going to be left with the value of phi at c minus the value of phi at a. So this is just the fundamental theorem of calculus, which relates gradients and areas. Now what we can do is we can extend on this here, and we can take the double integral of this function phi now with respect to dx and dy. So we know that this entire term here is equal to phi of c minus phi of a. So if we were to then go ahead and integrate that entire term with respect to now dy, then we're going to be left with, rather than the phi of c minus the phi of a, we'll have the integral of the phi of c dy of c minus the phi of a dy of a. So don't get lost in that, that's a very simple algebraic move. We've simply integrated what we have here on the left hand side, and we're going to integrate again what we have on the right hand side, and we're going to be left with this here. So let's take this and we'll continue on to the next page. So let's take this closed loop here in blue, and we'll call this closed loop gamma. Also, let's pick a direction which is, in this case here, it's the anti-clockwise direction around this closed loop. So it means that everything that's inside the closed loop will be to our left. So if we were walking around this closed loop, the inside would always be at our left hand side. Now let's take a line from A to C, which travels along parallel to the x-axis, and also a line from B to D, which travels parallel to the y-axis. So if we look at this point C here, and we are walking around the loop in this anti-clockwise direction, that means whenever we move along the curve here, we're going to be moving in the positive y direction. So we can say therefore that the dy of C is equal to the positive dy. And at the other side here, again, if we were walking around in the anti-clockwise direction, then this point here, A, is going to shift down by a value of minus dy. So we can see here that our dy of A would equal minus dy. Now we could do the same for this line here. If we were to start off at point D and we moved in this direction here, it would mean that we would be moving in a negative x direction. So this point here would be travelling in this direction here, which would be a minus x. So we could say that our dx at point D is equal to minus dx. And we could also look at the point B here, and again, as we moved around the loop here, the point B here would be travelling in the positive dx. So dx of B would equal positive dx. So that's just a simple bit of geometry. So we've seen this part of the equation in the previous page. This was just the fundamental theorem of calculus, but we integrated it with respect to another independent variable, in this case dy, and we got this here. But what does this tell us geometrically? Well, geometrically what it's telling is that if we were to look at the chord here, now that's a chord generated by this AC. Now this AC is going to vary by dy. So in effect, it's telling us that we're going to have a chord here which is going to run, for example, from, let's fix this out, it's going to run, for example, from this point to this point, and then it's going to go up by another dy, and it's going to move from this point to this point, and up again, and so on and so forth, until eventually it maps out the endpoints here of the chord will map out this closed loop gamma. So it means that this thing here can be rewritten as the integral around the closed loop gamma of our function phi by dy. Now that's it geometrically, but of course algebraically as well, we can see that this thing here is nothing other than the integral around the closed loop gamma over phi dy. Okay, so just this rewritten, and we take our endpoints here, but the endpoints here are going to map out the gamma. Now we can do this also with the respect to dx. So that we would have some line here dB, which is parallel to the y-axis, but it's going to move in this direction here, so it's going to go like this. So as it maps along in this direction, the endpoints, vertically, the endpoints are going to again map out this closed loop gamma. So we can copy what we have above, but we can redo it for a new function psi. So we'll end up with what we have above, but we're going to have our psi of d dx of d minus psi of b dx of b. Now again, we've worked our way round about that closed loop, but we have to be careful here because the value of our dx at d is now the value of minus dx, and the value of dx at b is plus dx. So it means that whenever we work through the signs here, we're going to be left with the closed loop of our function psi by dx around that closed loop gamma, but it's going to be a negative sign. So it means that we can rewrite this here. We'll just miss out the central part here, and we'll miss out the central part here. So we're going to be left with this function and also this function here. Now whenever we add both of these together, we're going to get back to our Green's theorem. Now that's a geometric description which splits down the geometry of this into a vertical component and a horizontal component, but we could also look at it in another way, in which we look at it in terms of a surface integral generating a line integral, and rather than looking at it in separate x and y's, we can just look at it as one whole entity. So let's go ahead and we'll just have a quick look at that on the next page. It helps to increase your intuition. So let's say we've got some closed loop. So this is our closed loop, and we can call that our gamma. Now let's say we were to create something called a capping surface on this closed loop. Now what I mean by that is, imagine this here is just the circumference, say, of your head, and you're going to put a swimming cap on. Then we could draw this cap out in a three-dimensional sense if we just draw these lines in. So this represents a capping surface round about this closed loop. Now if we, as mentioned previously, we're going to walk round each of these loops in the same direction, so we're going to go anti-clockwise. So if I went anti-clockwise round this loop here, and it would be anti-clockwise round this one, and this one, and this one, then we can see here that if we were to take these two here, then the line integral would be up along this direction and then this direction, and when we came to this joining point between these two, we would have a line integral which would be in this direction for this one, but when we come round this way, the line integral would be in this direction from this component. So both these line integrals here are going to be the negative of one another, so in effect they're just going to cancel out. So when we cancel out that one there, what we're going to be left with is the line integral round the larger outside block here. Now we could do the same for this direction here. The line integral for this component here is going to be in this direction, but for this one here it's going to be in this direction. So these two are going to cancel. So again, what's going to happen is all of these internal lines here in effect are going to cancel one another out. So all you're going to be left with in the end is the line integral round about the outer edge of this two-dimensional surface, the three-dimensional surface. So it's going to relate a surface integral with a line integral round about the outer edge of that surface. So that's all that Green's theorem really is telling us. So it's quite a simple geometric thing. So we can simplify it here by just putting in two blocks. And we can say that if we were to go round in this direction, and also in this direction here, then this component here would be in this direction, and this component through this block would be in this direction. So it means that whenever we add these two up, they're going to be the negative of one another, so they'll just cancel out, and this here would be equivalent to the line integral round about the entire block. And that's all that our Green's theorem here is telling us geometrically. So if you're interested in exploring Green's theorem and a few other theorems which are used within vector calculus, then I've got a full course on divergence, gradient and curl, which will get into this in a lot more detail. But let's take what we've learned here and our Green's theorem equation, and we'll use that in order to take the value of eta outside of the brackets. So thank you for listening to this video. I'll get you on the next video. Goodbye.